Okay, we have a 40 Newton weight, which is approximately a 4 kilogram mass. We're going to make this approximation. And we have a net force acting on this weight that's equal to negative 600 newtons per meter times y. Now we're going to release this at y equals negative 4 centimeters. And now that would be relative to the equilibrium point. Why? Because if y is 0, the net force is 0. That's the equilibrium point. So negative 4 centimeters, if y is negative 4 centimeters, that is negative 4 centimeters relative to the equilibrium point. We kind of want to understand that, but let's move on. Okay, so that our net force is mass times y double prime. And that's going to be negative 600 newtons per meter times y. Now we usually use the lowercase m for mass, but now we're using lowercase m for meters. So I used the clumsier shouting type capital M for the mass. We're going to replace that by the 4 kilograms in a minute anyhow. So there's an equation that expresses net force equals net force. Okay, well, we rearranged the equation. We put the 600 newtons per meter times y on this side. And we see we have a second order differential equation in y. We probably would have seen that here too, but we put it in this form because that's a form in which we will naturally want to solve it. Then we plug in the 4 kilograms for m, and then we divide through by the 4 kilograms, and we get this equation. Okay, so y double prime, 150 newtons per kilogram meter times y. I'm not sure what the difference is between this and this. Well, yeah, a newton divided by a kilogram meter is a kilogram meter per second squared divided by a kilogram meter, which is a reciprocal second squared, second to the negative 2. So that's the difference here. Then we assume that y equals ae to the rt, something we're very used to doing now, and we get a characteristic equation and we solve it. The solution to that equation that I'll allow you to write out and verify for yourself is y equals a times the cosine of the square root of this 150 reciprocal seconds times t plus b times the sine of that times t. So when we solve the characteristic equation, we're going to get an imaginary solution. We're going to use the Euler Identity, and this is going to come out of it in a way that we've seen repeatedly. Okay, well, the square root of 150 is about 12.2 ballpark. So there's our function, but of course we could express that as a single sine or cosine function, some constant times the sine of that angular frequency, 12.2 radians per second times t, plus some phase angle, so that the constants a and b on the sine and cosine here are related to the constant c we have here and the phase angle. And simple high school trigonometry, trigonometric identities allow us to figure out what c is and phi if we happen to know what a and b are. Now, we don't need to actually do that, because if we just use this as our solution, then we just have to identify the c and the phi that correspond to our initial conditions, which would be pretty easy to do. So we get this solution, and the solution looks like this. Now this almost looks like an arrow here. This is c, and this is negative c. Also, 12.2 radians per second is how fast? Well, 2 pi over 12.2 seconds is about a half second. So it takes roughly a half second for this natural frequency of this oscillator to complete a cycle. So from here to here would be a half second. Actually, a half second would go in this direction. And from here to here would be a half second. So if we happen to start at t equals 0 here, we go through 2 cycles in 1 second. Now we don't actually start here, we start at -4 centimeters, and that's actually going to be our amplitude, so we'd actually start here, and our C would be 4 centimeters, you can verify that, and we'd have a phase angle, because this is not the graph of just the sine of omega t. The sine of omega t would start at this point or this point, depending on how we set up our axis. Okay, it starts here. So that phi is either going to be plus 90 degrees or minus 90 degrees. So you can figure out what that would be. We could also have written this as negative c times the cosine of 12.2 radians per second times t. But you want to think through what that phase angle would be, whether it's plus 90 degrees or minus 90 degrees. Okay, well that's a solution of this equation. Now we're going to complicate the equation a little bit and say now our net force is the same, negative 600 newtons per meter times y, plus a driving force, a 10 Newton times a cosine of 13.5 radians per second times t. And now, we note first that 13.5 radians per second is somewhat different than the natural frequency of the system. So that the driving force is going to come in and out of phase with the natural frequency, or vice versa. These two, the driving force and the natural frequency, will keep coming in and out of phase, sometimes interfering positively, sometimes interfering negatively. Well, we solve the equation in any case. We write the equation, same left-hand side that we had over here when we got down to here. And of course, in the process, we're going to have divided the everything in this equation by the mass, the 4 kilogram mass, which will take our 10 newtons and reduce it to 2.5, 10 divided by 4 being 2.5, and since we're dividing by kilograms, our newton divided by kilogram leaves us a meter per second squared. So here's our equation. This is our homogeneous part, and we've already solved it. And this is our non-homogeneous part. So what do we have to do? We have to find a particular solution. So our characteristic solution is just our C. Now I wrote C sine of this, now I wrote C cosine of this. Let's be consistent, and let's make this C times the sine of 12.2 radians per second times t plus a phase constant. If it was a cosine, then your phase constant would either be plus or minus 180 degrees. Now, those phases would be exactly the same. Okay, so particular solution. We plug this particular solution in. So, the particular solution is going to be, okay, let's talk about why we have this. We have to get a cosine of 13.5 radians per second times t out of a combination of y and y double prime. Okay, the only function whose second derivative is a cosine function is the cosine function. And of course, the function itself is a cosine function. So we just have a cosine 13.5 radians per second times t. Now in general, it'd be a combination of a cosine and a sine of 13.5 radians per second times t. So we're kind of taking a shortcut. And it's not necessary to take that shortcut. You can include the sine in your solution. You'll find that its coefficient ends up being 0. And we've done a number of problems where that actually happens. So I think we're justified in taking this shortcut. Well, we plug this into the equation and solve for A. And then we see where that takes us, see where that leads us. Okay, well, we'll quickly do the solution for A. We do have a little more time on this video. Okay, so plugging this into our equation, we're going to have to plug its second derivative in for y double prime and its first derivative for y. I mean, it's the function itself for y. So we take its derivatives. First derivative, we'll get a negative 13.5 radian per second times a times the sine. And then the derivative of that, the chain rule is going to give us another 13.5 radians per second, so that we're going to get negative 13.5 radians per second quantity squared times a times the cosine, and I just wrote the parentheses, but the parentheses will automatically include the 13.5 radians per second times t. So when we plug that in, here's the equation that we get. Again, I haven't written out the 13.5 radians per second times t, but that's what's in every one of these parentheses. And just adding these up, we end up with what? Negative 13.5 radians per second squared times a plus 150 reciprocal seconds squared, which can be written as radian per second squared. Go back to what radians actually mean. You see that you can kind of bring them in and out whenever you need them. So we're going to have a multiplied by the square of this and this added to this, and that's going to have to equal 2.5. Now I've got meters, reciprocal seconds here, and it's written kind of clumsily. I'm not going to change it. This says 2.5 meters second to the negative 2, which means 2.5 meters per second. So it's kind of garbled here. Well, we're going to add up these two, and then we're going to divide by the coefficient of a to get a, and we get a equals 2.5 over negative 182 plus 150. I've estimated the square of 13.5 to be 182. So we're going to get our negative 182 plus 150 divided into 2.5. We're dividing reciprocal seconds squared into meters times reciprocal seconds squared, leaving us meters. So this is going to have units of meters. And when we divide this out, we get negative 0.08 meters approximately. Okay, so now we know our particular solution, and now what's going to happen when we put our characteristic solution together with our particular solution? Well, we will have to look at that in a subsequent video.